Hey, welcome back everyone, and today we're going to talk about the April Jane Street question, which is robot capture the flag. So in this question, we're given two different robots, Erin and Erin, so they have the same name, or the same sounding name, so let's call them A and B instead. So A and B have made it to this year's final, and in this question, they're situated at the center of a unit circle, and a flag is placed somewhere inside the circle. At location chosen uniformly at random. So it's often helpful for us to draw a diagram immediately. So let's draw a big unit circle here. These robots are initially all placed in the middle, so A and B are here. And somewhere on the circle, there's going to be a flag, and that's our goal. This is where we want to be. So let's continue reading the problem. So after the flag is placed, Erin is able to deduce the distance to the flag. So A knows how far it is from the flag, and what B knows, or what the other Erin knows, is the direction to the flag. So equivalently, Erin, or A, knows the radius, so A knows the radius, and B knows theta, or the angle at the polar coordinate of the flag's location. So both robots after that are able to make a single move after the flag is placed, if they wish. So any move is to be made without the knowledge of what the other robot is doing. So they do these moves independently and without seeing what the other robot is doing. So after this move, whichever robot is closer to the flag after these moves captures the flag and is declared the winner. So our goal with this single move is going to be closer to the flag than the other robot is. So also during the preliminaries, it's discovered that Erin, or B, is programmed to play at a fixed distance along the detected angle theta. So if we know this angle here is theta from 0, so B is always going to play somewhere along this line, because it's going to be optimal for B. So assuming otherwise optimal play by both robots, can we determine the probability, let's call that PA, that Erin will win? So we also want to express this answer to 10 decimal places. So this question requires us to be super precise about our answer. So right off the bat, we already have a preliminary little diagram here. We know that A and B both start from the center and they want to be as close to the flag as possible, or closer than the other robot inside of a single move. So A, it knows the radius r, and B knows the angle theta. So now we can take a look at what they will do. So let's actually clear up the diagram a little bit. It's a little bit clustered here. So we know that B will play at a fixed angle along the angle that it knows is optimal. So let's draw a little analysis here. We have two concentric circles. Let's call this circle the B circle. So the distance from the radius to the circle is going to be a distance of lowercase b. So this is how far B is going to go. So B is going to play at a fixed distance, so we can assume this is the optimal distance B can play. So A can, from B's point of view, can also compute what this distance is. So A and B both know that B is going to play this distance of little b away from the center. And it's always going to be along the optimal angle. It's always going to be along the angle theta. So just to erase this here, we know that from the center, B is always going to be playing the optimal angle theta. So now where should A play? Because first of all, A knows this radius r, and from B's point of view, A can also compute, if it plays optimally, this distance b. So A knows what the actual radius is. Let's say the actual radius is this blue circle right here. Let's make all these concentric. So A knows this blue circle as well as where B plays. So this blue circle, let's call this distance r. And these two lines are going to overlap because B is always playing at the correct angle theta. So now A wants to be closer to this flag. Let's draw a little red dot here. This red dot is going to represent the flag. So A wants to be closer to the flag than B is. So now A has a couple of decisions here. So first of all, suppose this r is really small. So instead of this big circle, let's say we have a smaller blue circle. So in the case that the radius is pretty small, where should A play? So we can see that the distance from B, this green X here, is going to be where B plays. So distance to the red dot should have moved Whoops. So the red dot should now be here. The distance from B to the red dot here is going to be longer than distance from the center of the circle to the red dot. So remember, A doesn't know the angle theta, but it doesn't matter what the angle theta is if A always plays at the center of the circle. So if A plays right here, right in the middle of the circle, then if this distance from A to R, or the center of the circle to R, is less than the distance from B to R, then what we want to do is we want to always play at the center of the circle if we're A. So A's decision tree is going to look something like this. First, it's going to check if we want to play at the center of the circle. So center of circle. And we want to do this if radius is less than B over 2. Remember, R, the radius, is the actual distance that only A knows. And if this distance is less than B over 2, that means B is going to be farther away from the actual goal than A is. So A is going to play at the center of the circle. So the distance from the actual goal for A is going to be R. The distance from the goal for B is going to be little b over 2. So R is less than little b over 2. That means A wins. So A wants to play at the center of the circle if little r is less than little b over 2. So what about the other case? Where would A play if, suppose, r is greater than b over 2? So let's draw another diagram to help us understand this different situation. So we know that A can't play at the center of the circle anymore because it's guaranteed that A's distance r is greater than b over 2, so A will lose if A plays at the center of the circle. So A could have another alternative. So let's draw a really big circle here. So, whoops. So in this big circle, let me move this circle out here. Suppose we have the center of the circle, it's going to be somewhere here. And we have the radius of the circle, which is going to be r. So now we know that this is where B is going to play. Sorry, this is the B circle. This is where B is going to play. Let's actually draw a green line to represent B. So now where should A play if A knows that R is pretty big and R is maybe somewhere along here? For example, this is where R is. And this radius is R here. So we know that for A to win, A has to be within this little circle's radius. Because this is, so from the center to the X point, that's going to be how far B plays. So B is going to be right here. The actual goal is going to be right here. This is the goal. Let's actually just draw that in red again. So for A to be closer to this goal than B is, A has to be somewhere within this circle that surrounds the goal. Let's draw a nice circle here. So A needs to be somewhere within the circle for A to beat B, because otherwise B is always going to win. So for example, if A played somewhere out here, then A is going to be farther from the goal than B is. So A doesn't want to play out there. That means for A to win, A has to be within the circle. And if A wants to be within the circle, A has to maximize the chance the circle falls on it. Because A doesn't know the angle theta, so A has to guess a optimal position to play. So we know that this little circle here, it's going to be somewhere centered along the line radius. So we know that the circle is going to go in a circle with equal probability at falling at every angle theta, since A doesn't know what theta is. Only B does. So how can A maximize the chance that the point it plays is going to be falling within this circle? So we know this circle is going to be circling somewhere around here. And because A doesn't know what theta is, anywhere it plays at any angle theta is going to have equal probability. So suppose this circle is here. Then if A plays at this point, let's actually draw it in a different color. Let's draw it in yellow. So this A point, if A plays here, A is actually going to be within the circle and A is going to win. So if the circle rotates up, 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 up here, and A plays within that yellow spot, then A is still going to win. So if A plays at this spot, A is going to encompass the maximum number of these circles along the radius for A to win. So now we can calculate the distance that A should actually play. And correspondingly, we can calculate the win rate of A. So we know that we can also draw a radius from the center of the circle all the way to this point, and this is going to have radius r. And correspondingly, this angle here, let's call this angle alpha. As long as theta falls within alpha, A is going to win. So this yellow line here, this is going to have, let's get rid of this arrow. So if A falls somewhere on this line, then A is going to win. And we can calculate how long this line is because this is the radius of the circle, although it doesn't really look like it right now. This is B minus R. Because the longer one is going to be, this entire thing is going to be B, this shorter one is going to be R, so the radius of the circle is going to be B minus R. So to calculate the angle alpha, we can just do simple trigonometry here. Alpha equals to arc sine of B minus R over R. So remember, it's also possible for our angle, so for our goal radius to be on the outside of the big circle as opposed to inside. So if it's outside, then we can just extend everything outside once, and this will be R minus B over R instead of B minus R over R. So to save us the computation of making another test case or a different situation, we can just write an absolute value around this. So alpha is going to equal to arc sine B minus R over R. So what is the probability A wins if this is the situation? Well, it's going to be 2 alpha because it could also be on this side, this angle is also alpha. So as long as theta falls within 2 alpha and theta sample size is going to be 2 pi because the whole circle is possible for theta. Theta is uniformly distributed and the whole circle is going to be 2 pi or 360 degrees. So the chance A wins is going to be 2 alpha over 2 pi. So now with this out of the way, the chance A wins, if it's the center of the circle, is going to be 100%. The chance A wins, if it's not in the center of the circle, it's going to be 2 alpha over 2 pi. So now we can create a solution for P of A to calculate the chance that A actually wins. So P of A is going to be, first of all, it's possible that we can just play at the center of the circle if the radius is between 0 and B over 2. So the probability that we win is going to be 1, representing 100%, or a guaranteed win. And we take the integral with respect to radius. So plus, so the other situation is if R is greater than B over 2, so B over 2 all the way to 1, and the chance we win is going to be 2 alpha over 2 pi. Remember we said alpha is equal to arc sine, so arc sine into absolute value of B minus R over R. It's going to be 2 arc sine this, and it's going to be divided by our sample size of 2 pi for theta. And it's going to be dr as well. So is this it for finding the probability of A winning? There's actually one more step here, because what we missed here is that R is not uniformly distributed. Because if we look at a circle here, just say we have any circle, and we pick a random point inside the circle, let's say here, there's a high chance this point has a large radius as opposed to a small radius, because every piece of area within the circle is going to have equal distribution for theta, but not for R. There's less points closer to the middle of the circle, because every same area has the same number of points. So there's going to be more points on the outskirts of the circle as opposed to the inside. So R here is not uniformly distributed. So we can't actually take the integral dr, because this is assuming that R is uniformly distributed from 0 to 1. So what should we do in this case? There's actually something we know that is uniformly distributed, which is the area, because we know the point is randomly and uniformly put inside the circle or the flag. We know that every piece of area has the same chance of containing the flag. So the area of a circle, remember, is pi r squared, and this is going to be uniform. So how can we choose a radius for us to create a uniform area? So if we know that if r is somewhere uniformly distributed from 0 to 1, and we want the area to be uniform, we can have the radius of the circle be represented as r squared. So radius, not r squared, but instead square root of r. So we know that since we're squaring this radius to find the area is going to be at a ratio of pi r instead of pi r squared. So if we use square root of r as the radius, this area, since we know that r is uniformly distributed, that means pi r is also uniform because we're just scaling by a constant. So this area here, pi r, is uniformly distributed. So from this, what we know is that we have to use square root of r as the radius instead of pi r. So how does this change our integral here? Well, instead of integrating from 0 all the way to b over 2, because initially we're comparing b over 2 is less than r, right? So now we're comparing this to square root of r. So this is the same as saying b squared over 4 is less than r. So we're doing the integral from 0 all the way to b squared over 4. So writing this integral here again, p of a, the chance a wins, is going to be 0 all the way to b squared over 4. The chance is still 100% dr. Plus, now we're picking up the integral at b squared over 4 all the way to 1. And the chance a wins is going to be 2 arc sine b minus square root of r, since we're using square root of r as the radius instead of r, over square root of r divided by 2 pi dr. So this is the actual integral, and this is our answer for the chance a wins. So to find the actual answer, we need to find the minimum of the curve and then compute the value of this curve. So we'll talk about that a little bit later, but first I want to actually present the official solution that Jane Street gave. So what I gave earlier here, the solution, it's the same numerical value, but it's a little bit more confusing since we have to find the square root of r, but the official solution from Jane Street doesn't actually need this. So from what they did was that they immediately looked at the p of a, and they did the same decision tree as I did. So first of all, we have a chance of a winning from playing at the center of the circle. So from 0 all the way to b over 2, a has a 100% win rate, but they multiply this by r. So here, let's actually indicate this 1 means win rate of a, and this r is the PDF of radius. So it's the probability that the radius actually falls at that spot. So plus, picking up from b over 2 all the way to 1, the area is going to be 2 arc sine r minus b in absolute value. B minus r is the same as r minus b over r divided by 2 pi. Again, multiplied by r. So just like before, this here is the win rate, and this r here is the PDF of radius. So because there's more probability of larger r's versus smaller r's, r at smaller radiuses from 0 to b over 2, this is going to be considerably smaller than this r here. This is going to be from b over 2 all the way to 1. So now this is the PDF of the radiuses. We need to divide this entire thing by the entire sample size. So the size of the sample size is going to be, or the size of the sample space is going to be all r's from 0 to 1. So this entire sum of integrals is going to be divided by the integral from 0 to 1 of r dr. So if we compute these two functions numerically, so this is my solution, this is my solution, and this is the official solution. So these two things are going to give us the same answer. To find that answer, we can plot these on a curve. So let's draw a curve here. This is going to be 1 over 2, 0. So if B plays in the middle, 1 over 2, A can just play somewhere super close to B, so they have an equal chance of being closer to the flag. So the curve is going to look something like this, where this is 1 over 2, and this is 1. So this is the probability of A winning P of A. And this is based on what B plays. So we want to find the minimum, since B is always going to play at a spot to minimize the chance of A winning. So we can set the minimum where the derivative reaches 0, so probably somewhere around here. And numerically computing, this point is going to be somewhere around 0.501307, and the height of this is going to be around 0.166186. So this is the chance A wins given B plays optimally. The question says A and B both play optimally, so this is going to be the chance A is going to win. So around 16.6%. To find this actual answer based on these two integrals, or any of these integrals given here, you can use usually a Python or coding technique, or in this case, I used a binary search technique. So we're not going to get into the code, but it's all on my GitHub. So to search for the optimal place for B to play to minimize what A gets. So that was the April question for Jane Street. Thank you guys so much for watching. Hope you hope to learn something, and I'll see you in the next video.